So just out of curiosity, who has heard of peer-to-peer mesh networking before? And I don't mean by me stupidly ranting about my topic today before actually coming here and talking about it. Okay, cool. I might actually be able to teach you guys something. So the definition that I stole shamelessly from the internet is that mesh networks are highly distributed networks which use special routing, and that's essentially the crux of it. In traditional networks and with the internet, the route that a piece of data, a packet will travel to be sent from one node to another is pretty much predetermined. And the majority of nodes are just either senders or receivers. You know, I want to send something to Christian, and it goes through a bunch of networks and routers and everything, and eventually it gets to him. But that's all I do. I send data and I receive data. So peer-to-peer mesh networks work a bit differently. So let's look at the mesh part first. What it boils down to is you have a network topology where all the nodes are not only senders and receivers of data, but also routers. So a packet can take any path and route through any nodes and any number of nodes to get to its destination. It isn't this fixed topology and fixed paths that data travel, which gives you a lot of advantages and a lot of problems. We'll be looking at that. Just a note I've added here, in some ways, the internet kind of can act like a mesh network, the internet we know today, because a lot of intermediate nodes do also route data as well as are the destinations of data. But that is in special subparts of the internet, like our mobile phones don't behave like that, for example. And then the peer-to-peer part speaks to, you don't need to be part of this more complicated or more extended network. It's you have two nodes, we're connected directly somehow, and we exchange data. And this is essentially where this problem statement that I was tasked with came up. So we're sitting here, we're both sitting in this room. I want to send a WhatsApp to Christian. And I go and I type it, and I can see him. He's right there, his phone is right there in his hand. And I type the message, and that message goes God knows where, to some 4G tower, and gets routed to some server, which is, depending on the application, not necessarily even South Africa, reaches that server, and another message gets propagated all the way back to 5 meters across, but it traveled this insane distance. And is this necessary? It works. It's the way we're doing things currently. It's the way the internet works, but is it the best way? Is there a way we can communicate without this? And when I say the traditional internet, I mean things like public IP addresses, getting your connection via an ISP, having DNS names for things, all that. So at some point we did take a step in the right direction. We've all done that, I'm sure, like, you know, before we had these things like Spotify and Play Music, I downloaded all the music I wanted on my phone, and I had it as files on my phone. And if you had a friend who had a cool music collection, you'd go through their phone and mark all the ones, and you'd go peer-to-peer Bluetooth, what, and send it. And you'd sit there for the half an hour that it takes to send all the songs you want. And that would be what you do. And that was kind of a step in the right direction. We realized that if we're in this close proximity to each other, we don't need to route our data through God knows where to get it to the people that need to receive it. There are easier ways. Now, this wasn't ideal by any means. You needed to pair, you needed to explicitly click and connect to that device every time you wanted to send something. It didn't give us this flexibility that the internet does of, my phone just has an internet connection and I can just send things. So, step in the right direction, but not perfect. So, what I'm talking about here today is peer-to-peer mesh networks. And this is essentially this network that gets built up. And it works over either Bluetooth or peer-to-peer Wi-Fi, or both. Depends how you want to implement it. But essentially, all devices that are within range of these, you know, communication means can connect to each other and can transmit data directly to one another without the need for some router, some central communication means. And just as a small note, the internet can form part of this. So it's not an either-or thing, right? I can be down there in the mountain where I don't have internet reception for some reason, and we can form a cute chain of people, all with a mobile device, just within Wi-Fi range of one another, and I can send a packet, and it can get routed up until here, until somebody who does have a Wi-Fi connection, and it can go to England, in principle, right? So it's not, that's just the point I'm trying to make. These two technologies are not exclusive, they can be used together. So, yeah, this is the picture I put in to aid what I just explained without the picture, but that's the idea. So, it forms this mesh network, and if this person wants to send something to this guy, even though they're not directly connected, he'll send it, and it can go through that guy and get there. It could also go like this, through to get there. There's no, you know, it's not necessarily a predetermined fixed path, and these are people walking around with mobile devices. This network's topology constantly changes. And this is also just, it'll be extended, and this could represent a larger network or some routing protocol or a routing device. Now this is all cool, and we can magically, you know, build up this mesh network and transmit packets, and the things just go where they go. But how do we actually build this, right? How do you, as a developer or as a programmer, go and sit down and write something that will route the packets in this way? It's complicated shit. It's really not that easy. But there are two main ones that I found in my research. These are both experimental RFCs. For people who don't know what RFCs are, they're basically the formal definitions of networking protocols that determine how we communicate. So email has certain protocols, SMTP, POP3, whatever, and exactly how those protocols work are defined in RFCs. So you first, you know, for some you need to do a handshake and a greeting first, and then, you know, you need to send this message, and the first number of bytes of this message need to be this and that. And that's essentially how we can communicate via the internet at all, is by having these protocols and having these sets of rules that like determine, cool, you know, it's an agreed upon standard. Otherwise we'd just be sending bits to each other, nobody knows what they mean, and, you know, we'd be loading shotguns to fend off mutants from our cans of spam because the apocalypse would have come. So, actually I'm getting ahead of myself here. So you have the two protocols. The first one is optimized link state routing, and the other one is ad hoc on-demand distance vector. So the two protocols work fundamentally differently. What OLSR does is it constantly broadcasts messages to try and maintain a global picture of what the topology of the network looks like. So all the nodes are constantly broadcasting messages and getting responses, and it kind of builds up this picture that's more complete in certain places and less complete in others, of what nodes are where and what paths data can take. So this obviously has the overhead of constantly doing the broadcasting, but what this means, if I want to send a message from this guy to this guy, I have a better idea of what the shortest path is to take to get there, because it's constantly trying to build this picture of what the topology looks like. The other protocol, ad hoc on-demand distance vector, is much simpler to implement, but the routing can take longer, and that is essentially when you just broadcast a message. You just send it to every node you're connected to, that node sends it to every node it's connected to, and so on and so on and so on, until it reaches the node that it's meant for. And this has its own problems. It's a lot easier to implement. It doesn't have the overhead of constantly being maintained, but it sends a lot of data unnecessarily, because you get a lot of packets that are not for you. The majority of packets you get are not for you, and are not necessarily, it's not necessarily even necessary for that packet to come through you to get to its destination. It's just wasted. And this is an inherent trade-off. You want the flexibility and the robustness of having this peer-to-peer mesh network that can just change on demand. New devices get added to it, get removed from it, but there are going to be trade-offs. If you have a static network topology in an office that a network admin plans, you know exactly where data needs to be routed, but then that's it. If you want to change it, back to the drawing board and you start over. So this is flexibility, but it's trade-offs as anything in this industry. So, some of the advantages of this. Oh, by the way, you guys feel free to ask questions throughout the thing. please do, otherwise it's going to seem like I highly underprepared the amount of content in my talk. So, yes, John.
So how do you plan for security on this? So the data being sent through, how do you verify that it's not being intercepted halfway through?
Well, the thing is, so it's, from that point of view, it's the same problem you have with any network that routes through anywhere. You don't necessarily own every node or know of every node that it goes through when you access Facebook, that your data travels through. So you would need end-to-end encryption algorithms to ensure that. So the data can route through anywhere. Anyone can inspect those packets, but it won't be meaningful to them. But in that sense, it's the same security problem. That's not a security problem. The packet sniffing, it's not a security problem that's unique to mesh networks. Cool. Goodness? All right. So, advantages of this thing. You can really add new nodes much more easily. I have touched on that. It is more resilient and fault tolerant. So, if you have, I don't think anybody does that anymore, but if you have a star network topology, right? Then you reach this point where if the one in the middle goes down, nobody can talk to each other. Now here, you have multiple redundant routes that you can potentially take. They're not necessarily all the quickest route, but you have multiple redundant routes that you can take to send a packet from one place to another. And what's really cool to me about mesh networks is they get faster the more nodes you have. So traditional networking, the more people use that network, the more data you try, the more nodes there are, the more congested it gets, because it's kind of these fixed paths, and everyone is trying to route through these fixed paths. Whereas here, the more nodes you add, the more routes you have, the more options you have, and the better you can route data and the more quickly. Disadvantages, and the main thing with this is how cumbersome it is. So implementing these protocols is not simple, and getting them to be quick and efficient is not simple. It will almost guaranteed be slower. And that's the trade-off. You get the flexibility, but it will be slower. Yes?
Is that dependent on how many nodes you have?
So, very much so, yes. And it is also very dependent on who's trying to communicate to who. So if you're using a peer-to-peer mesh network, but you're in direct range of the node you want to talk to, it'll be quicker, right? So it's just in the average case, because the route the data takes is more unknown, and because you either need to constantly have the overhead of maintaining or broadcast the message, it's going to take longer, potentially. But once again, it is on a case-by-case basis. This is just in the average case, but it's also, to be fair, I'm thinking of the average case for a messaging application, because that's the context in which I research this technology. So it depends what you're building. That's not a hard and fast rule, it's just a potential issue that you need to be aware of. Yes?
So if the network determines which is the shortest route to get to the other point, what prohibits the network from creating one of those nodes as a bottleneck? Do you scan what the latency is of a node and then redirect it to another node to reduce network strain?
So it's a valid concern, and that will apply to OSLR. So you're talking about if you're trying to maintain what topology looks like, and you're automatically determining all the nodes need to go through here. So it's possible for natural bottlenecks to occur. So if I can show you, for example, where's a good place in here? Okay, this is pretty spread out, but it is possible to have a node where this is the only connection between two subnetworks. So if anyone from here wants to talk to anyone from here, it all has to go through that node. And that can occur, and that is, once again, the more people use the network, the better it becomes. So if you have that scenario, there isn't really a way around it. In terms of building it into the algorithm itself, these RFCs are still experimental, and they really aren't hard and fast. And based on what I saw of them, you will modify your routing algorithm slightly based on the needs of your application specifically to avoid bottlenecks like that, for example. So it's a definite concern. There isn't a clear answer. It's more you have to keep this in mind type of thing and try to work around it based on the application that you're building.
So you limit like the amount of connections that is available on the node?
I didn't say you do that, no. It would more be, that could be a way to go about it. You just need to make sure that you don't cut off the only potential path that the data can take. It's more determining intelligent routes, not necessarily, even if this isn't the shortest route, you, to potentially have data be routed over a longer route just because it would be more efficient for the network congestion as a whole. So getting to practical applications, instant messaging, obviously as I mentioned, you can use this for file sharing. It is a bit more complex. It's easier to imagine using this for like kind of instant messaging sending, like I want to send one packet at a time to this guy. If you need to build up the stream, then it's going to be harder, but that can definitely be done. And then from that point on, is it banking, email, cat videos, ordering McDonald's, whatever you want to do, this is a different kind of network that can be used as an alternative to the internet, potentially. But it has all the problems I've set out. But this is not it's a routing protocol. Or not a routing protocol, it's a way of thinking about routing. It doesn't have, it's not this specific, like, you know, it's only useful for this sector of IT. It can have multiple applications. It's a better or a different way of routing data. And then in terms of what's already out there, so if you want to go and build this, what can you use? So Apple and Android have native libraries that you can use to connect devices peer-to-peer. How you would implement your routing, you'd have full control over, but you'd also have to do more. There are a lot of frameworks and SDKs out there that kind of claim to sort of be plug and play, like you can just, you know, buy this thing, download this thing, add it to your app, and then you have peer-to-peer mesh networking almost out of the box. None of them give enough information on their websites that I am confident that they actually work. It seems like one of those cases where the product is over-marketed and underdeveloped, and I haven't actually subscribed to any of the free trials and tried it myself yet. I meant to before this talk, but I didn't get around to it. And then, I don't know if any of you have ever heard of FireChat. It is an application developed by Open Garden, which uses exactly this protocol. So the idea is like an application, for example, in an earthquake or some sort of natural disaster where the internet in that area and the networking is down, say the cell towers, you know, fallen over or whatever. You can use this application to still communicate throughout the entire city by just using the mesh network. And it sounds really cool in principle, but I've played around with it a bit. It doesn't work quite as well. And I've watched videos online of people doing it with larger groups over larger scales, and this app works, but it doesn't always work as perfectly as they claim it should. And this is like one of the leading ones where people have actually implemented this technology and is trying to sell their product. So this tech is, I don't know if we just haven't figured it out yet, if people are just implementing it wrong, but it's really hard protocols to understand and to properly implement. So the stuff is out there, but just be wary of out-of-the-box solutions when it comes to this technology, because it's really hard. And if you wanted to try and do it at all, I definitely say implement it yourself from scratch. Yes.
I know they use it in like concerts where like there's a huge lot of congestions within people, and the network could be down, so they use it in concert. But it takes too long to receive the message, so I can see.
Yes, that's. Some of them have different flaws. So the message never gets there. Either it gets there half an hour after you sent it, even though it's supposed to only be a few hops away. So yeah, it's not perfect, but it exists if you want to check it out. And that is the end of my slides and the end of my talk. If you have no other questions. Yes, Shingai.
Yeah. Yes, this one. Cool. So, it's not a fully connected network in the sense that every node is connected to every node directly. I wanted to know, what guidelines do you use to actually, when you're adding a node, that I'm going to connect it to these nodes, or there's going to be a bridge between You know, you can't hear where I'm coming from.
So the whole idea of this technology is that there isn't any onboarding process. It adapts. So it's not like if you now, once you join this network, there's a specific process you need to follow. You just turn on your Wi-Fi, and the protocol picks up the Wi-Fi devices that are near you, they pick you up, and you become part of the network. And depending on which routing protocol is used, you can then become part of the network and send and receive data and also route data as well. Which is why, and even as I'm saying that, it sounds very magic-y. Like, it's like, oh no, you just turn on your Wi-Fi and the network consumes you. And that's why implementing these things are hard. But once again, I'll see you in a second. Once again, that's the idea. You can either then, if you're using OLSR, the broadcast will then also be sent to you, and you will also start broadcasting to tell the network that I'm now here, I'm part of you, and the routes to you will be built up. Or if the other protocol is being used, the broadcast will just reach you because the devices that you're in range of will know about you and also broadcast data to you.
So what is the implications on like privacy for like T's and C's for your phone connecting to this mesh network? Is there any type of consent that a user has to give to add his phone to this network? And should people know that their phone is connected to a network like this?
So I'm going to be perfectly honest on this. I was trying to dig really deep into the how do we actually do this. I haven't looked into the legal implications at all. I imagine that this will be necessary, that you'll need the consent of the user, because the main concern to me is that a lot of your device's processing and routing power goes to data that you don't care about at all. You're turning your phone into a router, which will drain battery, and there are all sorts of other implications. So it's definitely something that needs to be considered, but I haven't really looked at the legal implications, I'll be honest. I can only speculate. Yes.
Okay, cool. Well, my question is very simple. So is it possible that my package can be lost through the network? So let's take, I'm sending the message to the third node on that network. Then it happens that it just disappeared on the second node, depending on the route that it took.
Yes, it is. And the reason for that is that this network isn't static. So even if there is a path from your device to that device, when you send the data, that path might not still exist when the packet has hopped halfway towards its destination. So that is possible, and you do need to build in redundancy for that. It's not a reliable end-to-end connection. It's more of a I don't want to say send and hope, because it's not quite that fragile, but it is possible that it won't arrive. And that is part of what I imagine is a lot of the issues with existing apps, but also not. I think a lot of that is that it was implemented poorly because they're not testing that in scenarios where people are running around. It's literally like they stand 3 people in a line slightly away from each other, perfectly still, and just hope the thing arrives, and it still doesn't always. So they're not even testing this extreme case. When you give a phone to everyone on 2 rugby teams and they just run around and you see if you can route data. It's not that extreme, and it still doesn't work. So, yes, Kimby. Packet switching.
Is it like this? The shortest path?
I think you guys, to build up the shortest path. Well, that's up to you. So, did you guys come in when I mentioned the RFCs? So it's that. So this is just the approach. To actually determine shortest path from that, it'll determine what variation of this thing you implement, and that'll determine what info you have. So you can take the approach of kind of designating master and slave nodes, and the majority of nodes just know what their nearest master node is, and they send the data to that, and from that point on they don't really worry. It gets handled. Or you can kind of, if you know it'll be less nodes in a more confined space, like say university campus only, you can try and build up full paths. And then you can use the extras algorithm or whatever shortest path determining algorithm you want. Determining the shortest path then becomes separate problem from actually determining what paths are available. So determining shortest path isn't something that's inherent to this technology. Yes, Christian.
I just want to know, let's say for example you have two networks connected through one single node, so they'll create a contesting point, and that node goes down. Do you think it's possible to store any messages that's meant to go to the other network on like a border node, and when that node gets restored it still continues its path towards its destination?
It is, and at the end of the day, with these algorithms, you are unfortunately to some extent going to have to build in hard cutoffs. So if you're using the broadcasting approach, for example, when a packet arrives at a node, it broadcasts it. You can have a rule, for example, that it'll broadcast the packet it got to any node that it is currently connected to and gets connected to in, say, the next 5 minutes. That 5 minutes may be a bad hard-coded value, I'm just saying, and because people move around. So you got this node, you got this message, I sent it to everyone here. I walk downstairs, suddenly I'm connected to a new set of nodes, and I still broadcast that message. And that's why this routing can also be used without internet to, have to transmit data over longer distances. The Open Garden actually has like an explanation video on YouTube for FireChat where they have that scenario where a packet is sent, it kind of reaches a border node, but I don't think the fact that it's a border node doesn't necessarily have to be known. It's just an arbitrary node, and then that person gets on a ferry and goes to a different island, and then the message can suddenly get to who it was meant for, or the message hops until it reaches, and this is where it gets even more complicated, but until it reaches a node that has an active internet connection, and then you can actually route that packet over the internet, and it gets down again. And now I'm assuming you'll need some sort of server for whatever application you're doing. You can't just continue the mesh network approach once you hit the internet, but that is also possible. So it's not necessarily routing to the person you want to send to, it's routing to a node that has an internet connection. From there you can go. So it's very flexible and very vague. It's more an idea in some senses than a hard and fast protocol. That's why these RFCs are experimental, and that's why you do get slight variations of it, and you'll probably be best off picking the one that suits you best and modifying it even further from there for whatever specific application you have. This is not something like TCP/IP that can be used generically throughout the entire world, no matter if you're building an app, a website, or a web server. So, time.
Thanks, Reinhardt.